Okay, number 5. We're given a function for velocity and we want to find the acceleration and the displacement at 6 seconds. So remember, acceleration is just the derivative, the time derivative of velocity. So I can take this goes to 0. This is negative 3 meters per second squared. Derivative of that is 1. This brings out a 2, so I have 0.4 meters per second cubed t squared. Let's substitute in acceleration at 6 seconds is equal to negative 3 meters per second squared plus 0.4 meters per second cubed. Oops, pardon me, 2 came out, we got a 1, times 6 seconds. Right, the units wouldn't have worked. We got it. 6 times 0.4 is 2.4, so this is equal to negative 0.6 meters per second squared. We also remember that velocity is equal to the rate of change of displacement, and if I want to find displacement, the change in displacement is v dt, is the area under the velocity time graph, and I can take a derivative to give me my whole change in displacement. That would be an integral. So we take the integral x, displacement as a function of time, is going to equal the integral of velocity dt. And we go from 0 to time. Okay? So when we take the integral of that, we'll get 5 meters per second times time minus 3 meters per second squared times squared over 2 plus 0.2 meters per second cubed over time cubed times time cubed divided by 3. And so we can evaluate that, but recognize that we begin at a time t equals 0 at 10 meters. So I can go back here and add that 10 meters plus. And so when we substitute in for 6 seconds, what do we get? We get 10 meters plus 30 meters per second. The seconds cancel. That's meters. Minus 3 halves times 36 seconds squared. The seconds cancel. I end up with the meters. 36 divided by 2 is 18 times 3 is 54 meters. Plus, oh, this is going to be the hard one. That's 216 times 0.2 is 43.2. And we divide by 3 and we get 14.4 meters. Let's add those up. 10, that's 40, minus 54, that's minus 14, plus 14.4 is 0.4 meters. How close that came to 0. What a coincidence.